Today, we know of the three subatomic particles of the atom: the proton, the neutron, and the electron. However, for a long time, scientists have struggled with piecing together the anatomy of the atom nucleus, and only until the early 20th century was the neutron discovered, and it was made possible by the work of one James Chadwick. James Chadwick was born in the small town of Bollington, England on October 20th, 1891. He was the son of John Joseph Chadwick, a railway storekeeper, and Anne Mary Knowles, a domestic servant. In 1895, his parents moved to Manchester, leaving Chadwick in his maternal grandparents' care. When he was 11, he was awarded entry to the prestigious Manchester Grammar School. Unfortunately, his parents could not afford the fees and instead opted for him to go to Manchester Central Grammar School for Boys. He reunited with his parents and found that he had two younger brothers, Harry and Hubert. Sadly, his sister died in infancy. Later, at age 16, he sat for 2 examinations for scholarships to universities, and he won both of them. He decided to take up an education at the Victoria University of Manchester in 1908. Although he enjoyed mathematics and even plans on majoring in it, he was interviewed by a physicist who assumes he wanted to study physics. Chadwick was too shy to correct him, and so he became a physics major.
In 1908, age 17, he studied his university education. By the end of his first year, he was awarded the Higginbotham Scholarship to study physics. The physics department of his school was led by Ernest Rutherford, who had previously won the Nobel Prize for Chemistry for his investigations of the disintegration of elements and the chemistry behind radioactive substances. For his final year students, Rutherford assigned projects, and Chadwick was assigned to find a means of comparing the amount of radioactive energy between two different sources. Rutherford's idea of measuring in terms of the activity of 1 gram was unworkable, which Chadwick knew. However, he continued with the project, and his findings resulted in his first paper, which was co-authored with Rutherford in 1912. Chadwick eventually graduated with first-class honors. He continued to measure the absorption of gamma rays by gases and liquids. This resulted in a paper under his name alone, and he was later awarded his Master of Science degree in the same year. Another scholarship allowed him to study and research at a university in Berlin. He studied beta radiation under Hans Geiger, who invented the Geiger counter to detect radiation levels. World War I broke out, and he was interned at the Beryllium internment camp near Berlin. Following the war's end, Chadwick returned to Manchester to work with Rutherford in 1919, who was now in charge of Cambridge's prestigious Cavendish Laboratory.
In 1923, at age 32, Chadwick became the Assistant Director of Research in the Cavendish Laboratory. He continued his study of the atomic nucleus. During this time, many believed that there were electrons in both the nucleus of the atom and outside of it. Take carbon, for example. Many believed that the carbon atom had 12 protons and 6 electrons with an electric charge of positive 6. Outside the nucleus was another 6 electrons, which would make the atom's overall electric charge 0. However, Rutherford, Chadwick, and some believed that the existence of particles without charges was possible. Chadwick searched for the neutron in 1923, but did not find it and tried again in 1928 but was unsuccessful. In 1930, the German physicist Walther Bothe and Herbert Becher noticed that when they shot alpha rays at beryllium, it emitted a neutral radiation which could also penetrate 200 millimeters of lead. It takes only 1 millimeter of lead to stop a proton. Both of them assumed that this neutral radiation was a result of high-energy gamma rays. Irene Joliot-Curie, a French scientist and daughter of Polish and naturalized French physicist and chemist, Marie Curie, put wax in front of the beryllium rays. Irene and her husband, Frederick, observed that high-speed protons were coming from the wax. Both knew that gamma rays could eject electrons from metals, and it appeared as though this was the case for the wax. Chadwick, however, believed that this radiation was not a result of gamma rays. To eject protons at such high velocity, one would need enormous amounts of energy, around 50 million electron volts. The particles colliding with the beryllium only produced 14 million electron volts. Chadwick believed that the neutrons were responsible for the beryllium rays.
Chadwick got to work to test his hypothesis. In a vacuum chamber, he placed both beryllium and polonium together. While the polonium emitted alpha rays, it struck the beryllium, which then emitted the elusive neutral rays. Chadwick then placed a target in the path of the rays. When the rays hit the target, atoms were knocked out, and as a result of this, the atoms became electrically charged and flew into a detector. This detector consisted of a chamber full of gas, and upon passing, the charged particles were ionized. These ions would later drift upward toward an electrode, which Chadwick used to measure the current. Knowing this current, he measured the amount of atoms and their estimated speed. To put it simply, gamma rays could not explain the speed of the atoms, leaving the only good explanation to be the existence of the neutron. He noted that due to the neutron's lack of a charge, they were able to penetrate much further than a regular proton would. In 1932, in the span of 2 short weeks, Chadwick published his paper, The Possible Existence of a Neutron, which proposed that neutrons were responsible for the mysterious radiation. In May of the same year, he released another paper, more definite and titled The Existence of a Neutron, and by 2 years later, it had been established that the neutron was indeed a new particle, different from what earlier scientists have suggested. Chadwick's discovery of the neutron changed scientists' view of the atom forever, and his work awarded him a Nobel Prize in 1935. Scientists would soon realize the true potential of the neutron in nuclear warfare. He was knighted in 1945, and a year later he became the British scientific advisor for the UN Atomic Energy Commission. In 1950, he was awarded the Copley Medal of the Royal Society and would eventually retire in 1958.